The ESIP firm carries out the works on the project design documentation output, the manufacture and exploitation of high economical aircrafts with large fuselage and high carrying capacity without airfield takeoff. The ESIP firm performs all kinds of work with an effort of leading scientific and research, project and design enterprises of the aircraft, defense, and space branches of the industry working by the conversion programs. The ESIP air vehicles are the new generation of the transport means. The ESIP air vehicles have stub fuselage, which allows to unite wing and fuselage functions and to create air vehicles with carrying hull. The experiments proved the possibility to create the energetically advantageous flow regime for the model with a streamline without separation with the help of boundary layer control system. With the streamline without separation, high lift force is realized with low values of lift force coefficient owing to the large aerodynamically lifting surface of the model. The control system was worked out in wind tunnels. The experiments were done on the small and large scale weight and drain models in conditions imitating takeoff, free flight and landing regime regarding ground surface effect. On the large scale models, the experiments were conducted with working engines. The tests were done in free flight and near the Earth's surface flight regime with various airflow speed. The setting of the boundary layer control system was done in the process of the tests. The set boundary layer control system ensured the stable, energetically advantageous flow regime with a streamline without separation. The experiments with the streamline of the model without separation fully confirmed project aerodynamic characteristics of the ESIP air vehicle. On the basis of the investigations, the project aerodynamic characteristics of the ESIP model were defined to provide flight conditions in unlimited airspace with working BLC system. Aerodynamic forces and moments affecting the model with an air cushion in free flight were obtained. An air cushion allows to reduce cruiser speed by 2 times without losing the height. In the result of the investigations, the project aerodynamic characteristics of the ESIP air vehicles were defined for takeoff landing regimes of the movements on an air cushion. The project aerodynamic characteristics of the ESIP air vehicle indicate its high aerodynamic quality, static and dynamic stability, and good maneuverability. Flight tests of the large-scale radio-controlled model were carried out without an air cushion. During the model's runs on a runway strip, dynamic characteristics were measured, forces and moments affecting the model were stated, calculated values of the run's length and takeoff speed were specified. The model's behavior during the runs showed good stability in the flying and bank angles and maneuverability on the course with the help of internal rudders. During intensive runs of the model, radio control system and the boundary layer control system were worked out. The test pressure measurements on the afterpart surface of the model and the measurements of its takeoff run dynamics confirmed the efficiency of the boundary layer control system for creating the streamline without separation. The first fly-ups of the model confirmed the calculated values of the rung length and the takeoff speed, showed the dynamic stability in the lengthwise direction and good controllability along the lateral channel. Further flight tests also confirmed the sufficient level of the aerodynamic lift force, the low levels of the aerodynamic resistance, and low power inputs for the BLC system in order to create the stable flow regime for the model with the streamline without separation. The flight tests showed the stability of the model along the lengthwise and lateral channels, good controllability on the course and in the flying and bank angles. The model performs the steep glide slope landing with the intensive speed loss using parachuting. The radio control system of the model's movements and the engine system on every stage of the tests proved to be normal. The flight tests of the large-scale model are to be continued in order to work out the air cushion system for the landing and takeoff on any kind of airfield, including water. During the flight tests, it's planned to work out the braking regime of the model with the help of the air cushion without losing the height, and the braking with the descent regime while converting the BLC system into the regime of the partial flow breakaway. The ESIP firm started to design air vehicles with carrying capacity from 7 to 600 tons. In 1990, the project design works on small-scale models were accomplished. The ESIP L2 air vehicles, full weight 7 tons, is intended for 2,200 kilometers flying range with cruiser speed from 470 up to 650 kilometers per hour. The takeoff and landing of the model will be performed on any kind of airfields, including water. The takeoff speed of the model is 130 km per hour. The landing speed is 110 km per hour. In the mid of 1991, it's planned to finish the manufacture and to start flight tests of 2 pilotless ESIP L2 models. The air vehicle's flight will be done in the automatic regime according to the control system program. On the pilotless models, it's planned to work up the brand new design elements, including the boundary relay control system and the air cushion system. The ESIP models are the new generation of the air vehicles of high carrying capacity. High efficiency of the ESIP air vehicles was determined by high aerodynamic quality and relatively low weight. The large surface and plane of the ESIP air vehicles allows to perform the takeoff and landing on an air cushion and to use any kind of airfields, including water. The spacious inner volume of the ESIP air vehicles creates the conditions for providing high-quality service. On the base of the ESIP air vehicles, it's planned to design special transport systems for comfortable trips, transportation of overall size cargoes, for fighting natural calamities, fire extinguishing, and transfers of the mobile medical aid stations. The ESIP firm invites Soviet and foreign companies for cooperation.
Hello and welcome to Beyond 2000. I'm Andrew Waterworth, and this week, flying saucers. Are they flights of fancy or flights of the future?
We uncover the Russian project to send us all into the skies in these alien aircraft.
UFO sighting. It can be intriguing and frightening, and not the sort of vessel an Earthling would be willing to enter.
You could be forgiven for thinking that this looks like one of those unidentified flying objects that people see mysteriously hovering in the night sky. It doesn't look like a regular aircraft, and it's not. It's a revolutionary new design that rolls the fuselage and the wings into this unusual shape. Nicknamed the flying saucer, it could change the way we fly.
Maybe this looks more like a scene from a Hollywood backlot, making props for a B-grade sci-fi epic. But here in the Saratov Aeronautical Factory, southeast of Moscow, Russian designers are toiling away on this weird-looking alien craft that until now has been a well-kept aviation secret. One small and wobbly skip for the mini model built to test the notion of a flying wing, but it could just be a giant leap into an entirely new age in air travel. It's early days along the road to a manned flying saucer mission, but the theory is that an oversized flying wing would be more economical and aerodynamic than today's aircraft. And in typical Russian style, there's no need to waste time and money on computer-aided design to tell them that. The shape of the fuselage provides 80% of the lift by using the air sucked in along the top and through jet intakes. The air is blasted out the back, providing thrust, and underneath creating an air cushion, so there's no need for landing gear. The stubby wings and rear fins are there for control. The 15 by 11 metre 9-ton model is officially called the ESIP, and as you can see from this massive machinery and cabling, everything is inside the airframe.
One striking difference between this prototype and other aircraft is the location of its powerhouse. Rather than housing the engines on the wings, two standard jet engines are located right here in the cabin. By keeping them inside rather than out, the aerodynamics of the Taryelka remain as streamlined as possible.
The idea came from this man, Lev Shukin, the rocket designer responsible for the Russian half of the first international space link-up with the USA in 1975. With the help of aeronautical engineer Alexander Sodko, the design team are now refining the large prototype. Initial flight tests will be pilotless, but if all goes well, a manned model will be airborne in the next 12 months. This never-before-shown footage demonstrates a small model undergoing a series of tests in wind tunnels and on water to prove the aerodynamics of flight. Believe it or not, it's hoped the real thing will match the capabilities of a jumbo jet with its speed and altitude, and be capable of swift takeoffs and landings in almost any condition and without the need for a lengthy runway.
One of the most interesting places to use this machine is the southeast region of the world, in the island states. There, they can use it as a flying vehicle between the islands, where you need to take off from a ship, fly without going to high altitudes, and make a landing in a few kilometres.
Shukin came up with the first blueprints more than 15 years ago. He sees its role not only as a jet for up to 400 passengers, but also in specialist fields like a flying hospital theatre or for aerial fire control.
I have complex feelings for the project. On one hand, we really want this flying saucer to fly as soon as possible. But we also realise that because of the scope of what we're doing, there's more work to be done to make it happen.
More work and much more money. The team needs a cool $70 million to make the Taryelka a flying reality for people and cargo. One day in the future, when someone reports seeing a flying saucer, it may not be a case of science fiction. They may well be witnessing a Russian revolution in the skies.
Уточнение общих аэродинамических характеристик летательного аппарата в режиме свободного полета при боковой обдувке выполнено экспериментально по результатам продувок модели масштаба 1 к 5 в трубе Т-5 московского филиала ЦАГИ. Исследования проводились с работающей системой управления пограничным слоем, обеспечивающим безотрывное обтекание аппарата. Аэро- и гидродинамические характеристики изделия при взлете с воды и посадке на водную поверхность определились на основании результатов испытаний модели аппарата масштаба 1 к 5,6 в гидроканале московского филиала ЦАГИ. Испытания проводились на тихой воде и при наличии регулярной и нерегулярной волны. В процессе испытаний определилось влияние положения управляемых элементов воздушной подушки и величины наддува скегов на силы и моменты, действующие на аппарат. Отработка режима посадки включала в себя сброс модели на тихую воду и на водную поверхность с волнением. В результате исследований были определены законы управления аппаратом при взлете с воды и посадке на водную поверхность.
Аэродинамические испытания радиоуправляемой модели амфибийного варианта были начаты в аэродинамической трубе Т-3 для настройки системы управления пограничным слоем. Наладочные испытания модели проводились на акватории Нии-Геодезия. Первый этап испытаний включал пробежки по воде с различной скоростью для определения скоростных и маневренных характеристик.
Изготовление первого автоматически управляемого изделия ESIP L2-1 общим весом 9 тонн завершено на заводе научно-производственного объединения «Энергия». Сборка изделия производится на Саратовском авиационном заводе. В настоящее время завершены работы по подвеске двигателей и монтажу топливной системы. Смонтированы воздуховоды, системы управления пограничным слоем, а также оборудование для автоматического управления полетом и системы измерений.
Производится запуск трубы. Скорость потока максимальная 28 метров в секунду. Угол атаки 0 градусов. Избыточное давление активного газового вектора 1,8 атмосферы. по поведению лепестков можно заключить, что течение обтекания модели в основном безотрывное, включая третью и четвертую ячейки. Обтекание модели в основном безотрывное.